Good morning to all the participants. During the sessions, I request all the participants to please keep yourself muted, because we have done some settings here so that you can unmute yourself, so that during the question answers you can ask questions. But whenever the session is going on, just please unmute, please mute yourself, and whenever you want to ask any question at the end of the session, you can unmute and you can ask the session. So we have with us Dr. Chirag Thakur sir. So initially for half an hour, I will be delivering a keynote speech, or it's a kind of an introduction, and I will also give you a brief overview of what we are going to do during this FTP. And then after, I hand over the session to Chirag Thakur sir to discuss the IoT architecture in detail. So first of all, I would like to confirm whether am I audible or not. And I will start sharing the screen. So just let me know whether am I audible or not.
Yes, sir. You are audible, sir.
Okay. Thank you. Thank you very much, sir. So is my screen is visible?
Yes, sir.
Fine. Okay.
It is perfectly visible.
All right. Thank you. So first of all of you must be familiar, because you have participated in IoT, and all of you are knowing that IoT is a scenario where network connectivity and computing capability extends to the objects, sensors, actuators, and everyday items. So people are using internet, but IoT is a scenario where every objects will also use the internet and communicate the data. Sensor will sense the real world signals and will communicate to cloud. Actuators are also connected to internet, and they will actuate based on the commands given to them. So IoT is a concept in that everyday items will be connected with the internet, and they will also participate in exchange of information. So this is the overall scenario of IoT, where the first layer itself is a sensor layer, where job of sensor is to collect the data from real world and then communicate it to the cloud through various heterogeneous links. So this sensor layer is actually saying that all of the sensors are actually a smart sensors, and all the sensors are connected with internet. Now there are different applications are there. Suppose if I want to control some of the devices locally through my smartphone, then I may not go up to one. If even I have a Bluetooth link, I can use it within a home. Within a campus, sometimes we are satisfied only with the Wi-Fi, local Wi-Fi available with us. So if you want to control a devices within a campus, or if you want to send the data within a campus, then simple Wi-Fi will be also useful. That means our campus wide area network will be also sufficient. But suppose if you want to send the data remotely any part of the world, then we require in between the network layer, and you can see this is a heterogeneous network using a 4G, 5G, LoRaWAN, satellite communication, fiber optic communication. Professor Chirag Thakur will discuss more in detail about this architecture. Then all these mediums we are using to ultimately send our data to the cloud. And the last layer is the application layer. Application layer is very much useful, where different applications are developed for various sectors like agriculture, consumer, healthcare, transport, infrastructure, industrial, military, etc. It's not possible to list all applications here. Wide variety of applications are there for Internet of Things. So IoT is basically a kind of a multidisciplinary. It's not only a computer engineering, or it's not electrical engineering. It is not simply electronics engineering. It combines all engineering disciplines. So if you look at the elements of IoT, it is a devices called sensors. Then any type of connectivity, heterogeneous network. Chirag sir will discuss more about it. Then there are clouds and various protocols. So tomorrow again Dr. Chirag Thakur will discuss more about the protocols. Today itself we have a detailed session, session 3 by Dr. Dipesh Kamdar on the sensors and actuators. Then after getting connection, and when we send data to the cloud, now application layer, where all this data will be analyzed and some control signals will be sent to the actuators, where actually in application layer and actually there is a role of big data, then artificial intelligence, deep learning. So we will be collecting lot of data. So this IoT is not alone. IoT along with artificial intelligence and the data science all together are going in parallel. So IoT is a field where we require to work multidisciplinary. Only one discipline cannot work on IoT. We must have a good combination of electronics engineers, computer engineers, electrical engineers and other branches depending on the application. Because application is not only limited to electronics and computer, application is related to health, infrastructure. So every branch of engineering has to collaborate for this. So sometimes I call, it has provided opportunity for marriage between the different branch of engineering. So ultimately in elements of IoT, sensing and then communication through heterogeneous network, then we required cloud for storage and analysis, and then finally application for the end user. So in a sensor layer, we have actually sensors which will collect the data from physical world, smart devices integrated with sensors, and information like temperature, humidity, pressure, flow, air quality, motion detect, acceleration, vibrations, all these parameters will be captured and transferred to digital world, that is IoT systems, by smart sensors. So we have a hands-on session also. We will interface the sensors with embedded development board, and we will transmit this sensor data through Bluetooth link, through Wi-Fi link, as well as to the cloud. We will be using UB.cloud and ThingSpeak cloud. So session 3 is dedicated for sensors, where Professor Dipesh Kamdar will discuss all the sensors in detail. So these are the different sensors. You will be getting more details in session 3. Wide variety of sensors are available, and these sensors are useful to connect the raw data. Alcohol sensor, temperature sensor, rain sensor, PIR sensor, water flow sensor, then soil moisture sensor, which will be useful for agriculture purpose, distance measurement using ultrasonic sensor, proximity switch, thermistors, LDRs. And I was getting a message in WhatsApp that some of you have already purchased some of the sensors. So here we will give you live demonstration how to interface the sensors with your Node MCU board or a Raspberry Pi board, and then how to write program for it. So we have a separate hands-on sessions are also there, where we will be doing programming in MicroPython as well as using a Arduino IDE. So ultimately in a different sessions we will learn how to interface the sensors, then how to communicate the sensor data using heterogeneous link to the cloud system. And if you know the wide variety of sensors, again it can be categorized as a humidity sensor, moisture sensor, temperature, motion and velocity displacement, position, machine vision and optical sensors, acceleration sensors, electric and magnetic. So sensors are working on the principle of electric and magnetic field. Sensors are to detect the leakage in a pipeline, for the level measurement. Then force, load, and torque, so kind of a strain gauge. Then flow sensors, chemical and gas sensors, acoustic and sound vibration sensors like our ultrasonic sensors are based on that principle. So wide variety of sensors are there. Then there are many cloud computing services like a Microsoft Cloud, IBM Cloud, Amazon. We will be demonstrating you the ThinkSpeak and UB.dots. So we will be reading data from the sensors and we will upload it on these two cloud. And to give the more details about all these, there is a tomorrow first session is given to this IoT protocols, where Professor Chirag Thakur will be discussing all the IoT protocols. And then IoT is booming nowadays. Because why it is booming? Because nowadays we have a high speed internet available, and that's why IoT applications are increasing day by day. We have a LoRaWAN for long range wide area network is available with us. Low power wide area network, which is useful for IoT. We have so many Wi-Fi enabled devices available. We have a growing smartphone adoption. There are so many clouds which provides us storage as well as access data remotely. It provides facility. Then one more thing is increase in laziness. That is also one non-technical reason for the IoT applications, because we don't want to want to move from here and there, and we want everything centrally while sitting on a sofa set. So that's why that laziness also is one non-technical reason for that. Availability of low-cost Wi-Fi chip which can be attached with the sensor to make it smart. Some of you have already purchased the Node MCU. Some of you are already having in lab. It is costing around 250 rupees to 300 rupees. So it is a low-cost device available. That's actually one of the reason for IoT drivers. Low cost and small size embedded chips are available. And this is actually one simple IoT forecasting which was I was going through the Google, and then I found this chart that at every 127 IoT devices are introduced at every second. So every second 127 new IoT devices are connected to the web. And at present the number of IoT devices are around 30 billion. At the end of this December it will reach up to 31 billion devices. And it is expected that by 2025 total 75 billion devices will be there, IoT devices will be there. So there is a rise, continuous rise is there in number of IoT devices. So I have taken this data from this website. These are the IoT devices. Zigbee is for actually if you want to communicate through up to 100 meter range. Zigbee is good. Some of you have already purchased the Node MCU. The advanced version of Node MCU is the ESP32. In Node MCU there is only one analog channel. In ESP32 there are more analog channels are available. The clock speed of this ESP32 is double than the Node MCU. And one more thing, a very beautiful thing in ESP32 is that it has inbuilt Bluetooth module. In Node MCU, if you want to connect it with a Bluetooth, you have to purchase separate Bluetooth module, which you can connect with the Node MCU. While this ESP32 has Wi-Fi as well as Bluetooth, both are there inbuilt in this chip. Now suppose if you have a Arduino board which is do not have Wi-Fi chip in that, you can purchase separate ESP8266 which you can interface with the Arduino board and then you can use it. This is a Bluetooth module. If you want within home, if you want automation within a home, then Bluetooth itself is sufficient. If you do not want to send anything to the cloud, you do not want to send control the devices remotely from any part of the world, but within a home, if you want to control, then Bluetooth module is sufficient. Jetson Nano is a very good board, those who actually want to work on image and video applications. The LoRaWAN module, which provides a wide area network for Internet of Things. So these are the IoT devices. Low cost devices are available. Raspberry Pi costing around 3,000 rupees. Raspberry Pi Zero doesn't have a much peripheral on that, so it is a low cost compared to the Raspberry Pi board along with the peripheral. So once your prototype is ready, you can also use the Raspberry Pi Zero board. NetDuino Plus, Beagle board, these are the various hardwares available which we can use for the Raspberry IoT experiments. Few more boards, Arduino board which has a 8266 chip already mounted in that. So ESP8266 based Arduino is also available. If you have a Arduino Nano board, then you can purchase separate ESP8266 and connect with this Nano board to make because you will be able to connect the sensors and digital IO devices with help of with this Nano board, and then these devices you can connect with the internet through the Wi-Fi chip. So Nano board doesn't have a ESP8266, but ESP8266 you can connect with this Nano board. Then Arduino Nano board is also coming along with the Wi-Fi chip. So in that case, you need not purchase the chip separately. It is coming along with the board itself, so that you can write the program and you can connect the sensors, collect the data from the sensors, and send it to the cloud using this Wi-Fi module. Then Yun board, then Mega board. If your application is big, you want so many sensors to connect with cloud, then you can use the somewhat larger boards. If you want to control so many devices, then maybe you will need the Mega board. There are different IoT devices and sensors. Session 3 is dedicated for that, but just I will give the introduction here. Door sensors, PIR motion sensors. We will interface this motion sensor as well as temperature sensors during the hands-on session. We have a capacitive touch sensor, smoke sensor, temperature sensor. Then this temperature sensor provides us analog data. There are digital humidity and temperature sensors like DHT11 and DHT22 here, which provides you a digital data of temperature and humidity. These are the pin connections of that. Pin number 1 is VCC, pin number 2 is data, pin number 3 is not connected, so it's not useful. Pin number 4 is a ground. During the hands-on session, we will demonstrate how to connect this and how to write program for this. Then nowadays in COVID-19 situation, we need to measure the temperature, so remotely. So in that case, infrared temperature sensor will be useful. So it has a V in, that means VCC you have to connect here, ground you have to connect here, SCL, that is synchronous clock, serial clock, and SDA means serial data. So it will provide us I2C communication, inter-integrated communication. This we can also interface with the Node MCU, and this is very much useful in COVID-19 situation, because it will be useful for a gun temperature measurement. So it remotely you will be able to measure the temperature without any touch. Few more device, light sensors. Some of you have already purchased the LDR, flex sensors, accelerometer, particularly for the vibration measurements and tilt measurement. Hall effect sensors will measure the magnetic field strength. We have ultrasonic sensors. Basically, there is a transmitter and receiver. Transmitter will transmit the ultrasonic wave. If there is some objects is there, then ultrasonic wave will be reflected back from that object. So depending on how much time it takes to reflect back to the receiver, we will calculate the distance of that object from the ultrasonic sensor. So we will also demonstrate during our hands-on session how to interface this ultrasonic sensor. We have a ping device, again the same purpose, to measure the distance. We have a camera. If you want to send video data or image data, we can interface this camera with Raspberry Pi. So these are actually different things, and we have so many experts. who will be discussing all related IoT matters. We have two industrialists who will be coming to deliver the expert talk. Then we will have a discussion on MicroPython in one of the session. So you will learn a lot. It is not simply a a kind of a lecturing thing. There are also lots of hands-on sessions are also there. So you will learn a lot of skill during this entire 5 days program. So these are the references from where I have taken the content in this keynote speech. Thank you very much to all for joining with us. So let us learn together about IoT in 14 sessions. There are total 14 sessions will be there from different experts with presentation and hands-on sessions. Out of 14, there will be also one session for stress management, right? So I think now I will stop here. I don't want to consume more time of Dr. Chirag Thakur sir. Now I will invite Chirag Thakur sir to do the presentation. I will make you presenter, sir, so that you will be able to share your screen.
Sure, sir.
Okay.
GG, sir.
Sir, initially I am muting all because some noise is coming. So then after you can unmute yourself.
Okay, sir. Namaskar. Sir, can you kindly tell me that my screen is shared, my presentation is visible? Thank you, sir. Thank you very much. Namaskar. Welcome one and all to ATAL FDP on Internet of Things, and it is organized by, as we all know, EC department, that is Electronics and Communication Engineering Department, GEC Rajkot, Government Engineering College Rajkot. I personally thank our leader and our in-charge principal, sir, Professor Dr. C.H. Vitlani, sir, for putting GEC Rajkot on Indian map with this great start. And I hope in months to come, we all follow his footsteps and make more attempts and efforts to make sure that GEC Rajkot remains technologically relevant in the fraternity of academia and researchers. I take this opportunity to welcome all participants, distinguished directors, heads of departments, faculty members, researchers and professionals. I'm here to deliver a session on IoT architecture. Let us try to understand what is an architecture, but before that, I have an acknowledgement to make. Sir, am I audible perfectly? Okay, sir. Okay. So the presentation acknowledges content, especially images, which are taken from Google. So the default Google image URL is www.images.google.com. There are certain images which are Creative Commons. They fall in the field of Creative Commons, and there are certain images which are professional images. But the image source, as I told you, is images.google.com. And these images are used purely for an academic understanding purpose. So with that acknowledgement, let us salute and let us acknowledge the efforts of health workers, doctors, nurses, government staff, municipality workers, people who are putting great efforts to save the earth. Because we are having an online FDP, and because of these online FDP, the reason is we know there is COVID-19, and the whole world is right now going through that COVID-19 phase. So we hope that uh, the earth becomes one more time fully out of this pandemic situation, and we start removing our mask, making shake hands with our friends and colleagues, and spending time more with our family members and loved ones outside. I have the tendency to start my presentations with some of the marvelous quotes. So the first quote is here: "The purpose of education is to replace an empty mind with an open one." We all are academicians. We are associated with academia since long. So it is always our endeavor to replace an empty mind with an open one. This quote is from Malcolm Forbes. And there's another quote: "The thing, obviously not the Internet of Things wala thing. The thing about smart people is they sound crazy to dumb people." This is from one of the innovator, one of the path breaker, Mr. Steve Jobs. So with that, uh, let me switch over to the quotes from industry. These are certain quotes from industry regarding IoT. So I'll read a couple of them. IoT is a world where things like devices or sensors are connected and are able to share data. This is from MIT, one of the faculty of MIT. There's another one from Gartner. Gartner says the Internet of Things brings the power of device ecosystems to your enterprise. The power of device ecosystem. And I have a slide which shows the device ecosystem, and it shows the table also for IoT. There's a quote from one of the industry leader, Microsoft. The Internet of Things is all about the invaluable insights enabled by harnessing and analyzing the data from the connected devices. And then Cisco actually talks about Internet of Everything. I have a slide for one slide for Internet of Everything at the end of my presentation. So, why Internet of Things are there? First, we need to understand, and then we will try to understand what do we mean by an architecture. So first, we will try to understand why Internet of Things are there. Then, obviously, the basic understanding of ICT, and I'll also show you the presentation flow. But before I switch to my presentation flow, please bear with me. Digitization, then digitalization, and then digital transformation. So digitization is all about the earlier days, the 70s and 80s, where computers started getting the adoption in society. Henry Ford says that I want to park one car in the front of every house of America, and that's how he brought the automobile revolution. Mr. Bill Gates, William Henry Gates III, he said, I want to put a desktop PC on every single desk working person. That's what brought the digitization. But digitalization is all about the social networking sites where people became not only consumers, they transformed into contributors. We started contributing, and we will discuss this in a greater detail. Proliferation of social networking sites has made the data, the content, a central entity, and people who are just consumers in the static web era and the dynamic website era, who were just consuming, because there were a handful of people who are uploading content on internet, on web, www, and people, a large number of people used to download it. They used to consume the data, but they were not contributor in a better sense, in a larger sense. So digitalization is nothing but social networking sites, and this has made like WhatsApp, Facebook, and all this, where we upload our photographs, our lights, and all this. So that is digitalization. So from digitization to digitalization. And from digitalization, now we are entering the era of called digital transformation, where we want to make smart tables, so that if I put my mobile phone on a table, the table has a user interface through which I can transform the content. I want to create user interface with every single entity or object, or let us say thing, to make it more smart. Now, what is smartness? Yeah, what is dynamic user interface, which will make these objects a part of Internet of Things? If I can control my microwave oven from my mobile device, I can say that yes, my mobile device is connected to my smart microwave oven. But if I can control my microwave oven from my treadmill uh, screen, or my treadmill screen, then it is IoT. If I can control my refrigerator items from my sofa set in user interface or smart interface, if I can control my refrigerator temperature, uh, or the inventory in my, if I can place an inventory order without visiting my refrigerator from my sofa's side panel, then I'll say that it is Internet of Things. So just controlling microwave oven or your car from your mobile device is a baby step. But digital transformation is new type of structures and new hybrid models. Hybrid model talks about heterogeneity, and that we are going to discuss in this lecture, IoT architecture. So with that brief note, the same slide talks about restructuring of economic institution, because we are having very tall claims from MIT, from Cisco, from Microsoft about the number of billion number of devices connected to internet. And it is, as sir rightly said, 120 devices every second is getting connected. So our IoT world is actually getting bigger and bigger, and actually it is giving us a great opportunity as well as great challenge how to address it. And that's why IoT architecture is important. So this is what I talked about, like 50 devices. Now before I discuss this presentation flow, let me tell you that IoT started in which year. So I'm very happy to make you understand that online there was a paper in 1962. It was a seminal work. It was presented by, this was a research paper. It was presented by JCR Leclerc and Weldon Clark. And he wrote a paper in 1962, which is a seminal work. And the title was Online Man-Computer Communication. I repeat, the title of this seminal work research paper was Online Man-Computer Communication. And then after 68, there was another research work getting published. So what is important? Why internet protocols or internet architecture is important? Because see, IoT architecture is important because it is the next giant leap after internet. Sir Tim Berners-Lee, who is the patron of making this World Wide Web a feasible entity. See, there were devices in terms of thousands and lakhs who were connected, and we call these devices hosts or nodes. But the situation is not going to remain the same. Why we talk about IoT? Because internet is very famous. Internet is there in day-to-day use. And what is the definition of an internet? The definition of an internet says it is a computer network consisting of a worldwide network of computer networks that we use the TCP/IP network protocols. So it is TCP/IP, HTTP, these protocols are there. And technology is evolutionary in nature. They are not revolutionary. What is revolution? We had an old king and we replace it by a new king. Revolution. Chinese revolution, Russian revolution. Technology is not revolutionary. Technology is evolutionary. And because it is evolutionary, we will have coexistence of TCP, IP and HTTP along with this new set of protocols, along with this new set of IoT architecture. And that is why understanding internet definition is very important. The computer network consisting of a worldwide network of computer networks that use TCP IP network protocols to facilitate data transmission and exchange. So that is the conventional definition of internet. But that conventional definition of internet is not going to serve the purpose. We need to first understand the networking evolution. So networking evolution is going to be my first focus area. We will try to understand computer network's journey from local area network to web of things in very small span of time. Then we'll try to understand basic understanding of Internet of Things. Sir has already discussed a couple of definitions, and I'll add one or two slides to that. Then we'll try to understand IoT layered architecture. And then we'll take one 7-layered approach, IoT 7-layered approach, as our central theme of this session. Then we'll try to understand these layers and we'll try to understand their working also. And if time will permit me, I'll also take IoT industrial case studies to understand that how this architecture actually plays its role. And then the last slide, as I told you, it would be about Internet of Everything. It's a slide from, it's a vision from Cisco. So with this presentation flow, let me formally start. So before I start explaining the content on the slide, let me try to make you understand what is an architecture. So architecture is the process of development of methodical IT specifications, models and guidelines. So we all are aware that OSI reference model, starting from physical layer to application layer, it's been very successful, and there are protocols for every layer, because with every layer, the task is well specified. The protocols are well defined and the products are well developed. So when the tasks are well specified at every layer, when the protocols are well defined at every layer, and when the products are well developed at every layer, we can make that technology paradigm into reality. So same way, IoT is not a buzzword. IoT is a complete technology paradigm. It's a complete technology platform. It's a complete technology model. So for IoT also, every single layer and the functionality of that layer should be well specified. The protocol should be well specified, well configured, and the products which the companies are going to make for those layers, those interfaces, those development, those applications, they need to be well developed. And once we achieve these three with every IoT single layer, architectural layer, then only we can say that yes, IoT has arrived. And it is the process has already been started. We are not predicting the future. It is the present, and this present is having very rosy picture in terms of transforming the digital transformation. So technology architecture, when I say methodological IT specifications, models and guidelines, technology architecture mein kya hota hai? What technology architecture actually includes? So technology architecture actually includes framework. It includes standards and specifications. It includes development environment stack. Complete development environment stack is always part of technology architecture. So once we have this architecture well understood from our end, technology architecture, what does it provide? Technology architecture actually provides a more concrete view of the way in which application components will be realized and deployed. Because in Internet things or in Internet of Things, there are three major words which are important: design, development and deployment. We need to provide, we need to design objects, we need to design the new formation of objects, their related protocols, their applications, APIs, user interfaces. We need to design them. Then we need to develop them. So whatever object or protocol or specification or configuration we have designed, we have to develop it using the latest available technology platforms, software development kits or environments. And then we need to deploy it. Now, when you deploy it, Yes, yes, sir. Is it fine, sir? Okay, okay. So then there is the issue of deployment, because I told you when we discussed internet just few minutes back that we do have internet where nodes and hosts are connected. IP is taking care. IP address is 32-bit IP address is taking care, and now we have IPv6 also. So thousands or millions of devices are there. But when we move to transform from millions of devices to billions of devices, and these billions of devices are not going to be always having computational power. They are going to be constrained, this, and we will discuss this constraint in tomorrow's lecture when we will discuss the protocols, that what do we mean by constrained devices. Constrained devices are devices which has limited processing power, which has unreliable networking, and which has low power, like so that they can be operated by batteries. So when I need billions of devices to be part of Internet of Things, and majority of these billions of devices are constrained devices, as I said, limited processing power, unreliable networking. What I want to say is it's not always 24/7 reliable networking. They are on move. They connect to network, they leave the network, and low power. So when we try to deploy Internet of Things protocols and specifications and technology with this constrained devices, when we want to connect these constrained devices in this IoT uh, fraternity, there are challenges, and this challenges actually is very important, because we want billions of devices. I need smart interfaces where objects, where sensors and actuators actually play their role, and that's why these 7 layers are important. There is a 3-layer architecture also, there is a 5-layer architecture also, and then there is a 7-layer architecture also. I have a slide for that also. But before I go to that slide, evolution of Internet of Things is very important for us to understand. In the pre-internet era, we were more, it was more connection of human to human, and there was a telephony, there was an SMS, and we just wanted to talk to people. There was more of verbal communication, there was more of uh, getting connected, one human getting connected to the second human through SMSs or through mobile telephone. Then came WWW, World Wide Web, that is the Internet of Content. And why we call it internet? Internet stands for internetworking. So email, information, I told you that very few people used to create presentations, or they used to upload stuff, and using FTP protocol we used to download the stuff. We used to download those documents, those presentations, those web pages, those forms which were available on internet. So internet of content. और उस वक्त क्या था, smart and IT platforms were getting developed, and this is the era WWW, which has two minor phases. One is static web pages, and then dynamic web content. So dynamic web pages also dominated the world. But then came Internet of Services, which we call Web 2.0, where we talked about e-commerce. I just wanted to make an online purchase, online reservation, online product verification, online filling the form. I can fill the employment form or examination form online. Social. So that is Web 2.0. If I talk with respect to that of computer languages, the scripting languages actually played a pivotal role in making this this e-productivity and e-commerce getting realized. And actually, we moved very easily from smart computers to mobile phones. And this m-commerce actually started playing its role, where we were able to do a lot of web-based activity using this. But then came Internet of People. This is Internet of People is actually smart devices, objects and texts. This is the era of social media, which I just few minutes before told you that social networking sites, social media played a very major role. Skype, Facebook, YouTube, Twitter. These are the major examples of this, where they connected internetworking of people. So from pre-internet phase, internetworking of people, that is social media. So how actually social media played the role? The major change social media brought is now our internet, now our devices, they are 24/7 connected. If I give you a very small example, see, when you were, layman's example, when you were in the era of internet of services, we used to buy 2 Gbps bandwidth, internet bandwidth for 1 month, and all our internet based activities were taken care of, even though we are a professional. But when internet of people came, social media came, it became 24/7 connectivity, scalability. So there you started buying 2 GB of bandwidth for every day, which is now 4 GB or beyond 4 GB. So social media has put this consumer as a contributor. You started uploading your own photographs on Facebook. You started uploading your own YouTube videos. You started watching various YouTube videos, and then the Amazon Prime and all this came. So internet of people, where smart devices are there, objects and tags are there. If I talk about industry, RFID tags and other related stuff actually. But now we are moving towards internet of things, which is machine to machine. Now I want machine to talk to another machine without human intervention. This is where cloud computing comes. This is where big data comes. This is where service-oriented architecture comes, because smart objects, smart services are actually playing its own role. So it is data, and where semantic web is important, contextual data is important. So Internet of Things is all about machine to machine. Now this journey doesn't come very easily. See, pre-internet phase to Internet of Things, actually we started with network. So what is the conventional pedagogy definition of computer network? It's a collection of connected systems to share information and resources. That is like pre-internet era, local area network, metropolitan area network, wide area network. From this, actually we came to internet networking, and then came web of things. And web of things is actually where we started having more than one devices in our pocket, and we started consuming social media and all this, and we became contributors. So the whole consumer community is now contributor community, and this contributor community in social media will go one step further, and this contributor community will have more and more number of devices getting added to it. Like the car has more Internet of Things attached things or objects. Sensors are there, actuators are there. Sensors, physical quantity to digital quantity, actuators, digital quantity to physical quantity. So there are sensors, there are actuators. So your car will have more sensors than your home. Your home would have more sensors than your office. Your office would have more sensors than your company environment or your shop floors. So that's machine to machine interactions. So Internet of Things is very important with this. We started our journey with a conventional computer network, which said local area network. But then we came to metropolitan area network, wide area network. We started getting protocols like SOHO, small office, home office, or personal area network. There are protocols which we'll discuss tomorrow, where personal area networks are taken care of, where more than one devices are being connected, so that I can use my tablet, my desktop, my laptop, and my mobile phone simultaneously, machine to machine, and I can get them connected to the devices which are there in my vicinity, which are there in my neighborhood or surrounding area. And this actually will make sure that IPv6, the objective of IPv6 actually gets served. So that is something which is very important. So with this brief, let me move to the next slide. So we are here to discuss various stages. Now, before I try to make you understand these stages, there are three categories of devices, like big things, small things. So it's not that all devices or all things are always connected to internet. There are certain devices which we call non-IP things. So there are certain devices like big things. What do you mean by big thing? Because we are discussing Internet of Things. So big things are big in terms of complexity, processing power, computational capability or computational ability. The example is like router or a connected car. There is no power problem, there is no bandwidth issue, and there is a classical device management associated with router. It is always there. There are certain small things like I told constrained devices. There are sensors and smaller devices. But there is a third category of devices. We call them, it's a third scenario. And this third scenario is going to dominate the IoT world. And it is those non-IP things. They are very much part of IoT. Non-IP things. It's not always that all devices have TCP/IP capability, or all devices actually support HTTP directly. Not necessarily. That's why we call them non-IP thing. But this I is very much missing in this in non-IP things, IoT devices. They are not always connected, or they are not connected to internet. But yes, they support Zigbee or LoRa. And for them, we need gateway that we will discuss tomorrow. But here, the stage one is all about. So with that brief, let us try to understand stage one. Stage one is all about sensors and actuators, wired as well as wireless. Sensors, as I told you, the physical quantity to digital quantity, actuators the other way. There are certain coexistence of these sensors. They coexist. They all measure temperature, and then you need some kind of local processing, which we call edge computing. Stage one. Stage two is all about data acquisition systems, where data aggregation is important, control is important. This is the place where I try to accumulate, as I told you, that perhaps you are measuring in an industrial environment with a chemical critical system or some kind of mechanical or auto related system where pressure gauge need to be, they are very sensitive, they are quite fluctuating. So I need multiple data acquisition systems, and then I need to go for data aggregation environment or some kind of control machinery or mechanism, and then a local edge IT, pre-processing analytic part. Because if I have lots of devices or millions of devices in an industrial environment like Reliance refinery or some kind of automobile workhouse, I cannot put all this collected sensor data directly. I cannot upload that directly onto the internet. What I can have is I need to have pre-processing kind of or local processing kind of stuff, which we call edge computing. And then this data is to be uploaded on data centers or cloud for archival purposes, for management decisions or business intelligence, for analytics purpose. So that is stage number 4. So we have stage number 1, stage number 2, stage number 3 and 4. Now all these stages we need to have a layered approach just to understand how it is going to actually work. So before I go to that layered one, we are more interested control, calibrate, communication, communicate and collaborate. Now let us go back to stage number 1, 2, 3 and 4 and let us try to understand these 4 C's. What are those 4 C's? Control, calibrate, communicate and collaborate. So here you can see stage number 1 is all about control, then comes calibrate, then comes communicate. Before communicating, some kind of analytics, some kind of pre-processing, and once I communicate, collaborate. So these 4 C's and these 4 stages are very important. And once they are there, these smart objects actively can collaborate with other physical and virtual resources available in the internet. Because it's not always cloud upload. Sometimes they need to actively collaborate with other physical or virtual resources which are there in the neighborhood or in the vicinity of that industrial environment or the office environment. So collaboration is the punchline. It's the main phrase which we need to understand. So once I understand these 4 C's, I can have the formal definition of Internet of Things. Now, what does it say? It says the Internet of Things is the intelligent connectivity of physical devices driving massive gains in efficiency, business growth, and quality of life. Now, this is called QoE, quality of experience. QoS, we understand. QoS is all about availability, fault tolerance, maintainability. These are the conventional QoS parameters. There are many more also, but I'm just naming a few. But quality of experience is something which is very important. I'm watching a YouTube video, and I don't like jitters, or I don't like low bandwidth. I'm connected to each one of you across the length and breadth of India, and I'm delivering a lecture from this place, small town in Gujarat, and I'm reaching out to each one of you, and you, or neither me nor you, prefer any kind of jitter, any kind of internet connectivity issue. So efficiency, business growth, and quality of life. So Internet of Things is all about bringing quality of life. It's all about QoE, quality of experience, and the quality of experience not only adds to the joy and entertainment of people. Quality of experience has its own meaning in industry. Right information to the right person at the right time for the right decision is Internet of Things. Internet of Things can bring this. So control, calibrate, collaborate, these all are very important parameters. And that is why before I move to the conventional this is an IoT slide sir has already discussed, but I'll just try to repeat. There are certain very important objectives for an IoT. Number one, global network infrastructure. We all know this. Self-configuring capability. It's a major goal to achieve for any IoT system or application developer. Self-configuring capability. Whether it is at the sensor end, or whether it is at the edge computing end, or whether it is at the analytic part. Self-configuring capability. It is based on standards and interoperable communication protocols. We'll discuss them. There are physical and virtual things. There are certain things which are physical. There is a complete technology paradigm or model taking place. It's called software-defined network and network function virtualization. And software-defined network and network function virtualization has its own role to play in Internet of Things, because we are trying to create many virtual objects from the existing limited physical objects. And these virtual objects using NFV is going to create a very large pool of devices for us in an industry environment or in a professional environment. Likewise, software-defined network. A lot of hardware capabilities need to be controlled using this data plane and control plane and application plane, which are very much part of software-defined network. So physical and virtual things have their each role to play. What is an IoT? The objects have identities, physical attributes, and virtual personalities. So I told about developing a smart interface. What is an interface? Through which we interact. And when I say we, it is not limited to humans, it is limited to machine. So a machine can interact with another machine. A machine can collaborate with another machine. A machine can fetch data with another machine. So that is, and for that, that's why I told intelligent interfaces. So intelligent interfaces are something which is very crucial. Once I have intelligent interfaces, I can be very sure that yes, now I can interact with this device. I can collaborate with this object. I can collaborate with this thing. And once I achieve that intelligent interface, physical attributes and identities, then I can say that these devices or these objects or these things are seamlessly integrated. And once they are seamlessly integrated, I can derive business acumen out of it. I can derive professional features out of it. And these professional technology features, these professional features can help me to take better business decisions, be it sensors, be it alcohol sensors, be it any kind of pressure gauge parameter in a chemical industry. And once I create this seamlessly integrated IoT, I can create a very large information network. which is a content-driven information network. And this content-driven information network can give us better contextual information, because contextual information is very critical. There are certain data objects which are sensed periodically, and they are not very critical. But there are certain sensor inputs which are very critical, because if I talk about refinery, suppose you are having a very big tank and which is taking care of 90% of the production of that refinery, and there are sensors associated with that. So in distributed control system or a SCADA system, those sensors need to have utmost priority, and perhaps you are measuring them 3 times a second, and controlling them is, if you do not control them in time, a disaster can take place. So I need to build a very robust and very scalable information network. And Internet of Things, actually, through sensors, through actuators, basically what we try to do is we just try to propagate this information network to a larger horizon, be it industry setup or a chemical factory setup or an academia. So this is the periodic table for IoT, and I told you that here we can see a very well thought out. I apologize for the very small font size, but the periodic table of IoT, we are aware of the periodic table of that chemical components, chemistry, but there is a periodic table for IoT also. This is just for your reference purpose. Now we formally go with the architectural part, layered architecture. So there can be a 3-layer model, there can be a 5-layer model, and there can be a 7-layer model. Now here you can see the bottom part. It talks about, in a 3-layer model, there are things, then there is a cloud, and then there is an application. And these applications are for various purposes, and accordingly the symbols are also being placed. There is a stethoscope which talks about medical application, there is a car, there is a truck, there is an online purchase, there are books, there is a medical application, there is a smart house. You can, so these applications are there. So when Internet of Things is not necessarily that it has to be a 7-layer model or it has to be a 5-layer model. No, depending upon your requirement, depending upon the setup with which your object is getting integrated, or you are working with the object, it can be a 3-layer model also, where things, cloud, and application, these are the 3 layers. But when we expand this, we come with 5-layer model where objects are there, and these objects, there are multiple objects, and because there are multiple objects, we expand this cloud layer into this middleware layer, and this middleware layer is made up of 3 sub-layers: object abstraction, service management, and service composition. And if you recall can recall service-oriented architecture, which I just mentioned, service-oriented architecture actually talks about consuming services, and that is very important, where I consume services, and these services are in a composite manner also. So I can have a portal from where I can get the temperature also, and I can get the news also, and I can get the updates also. I can get the cricket updates also. So that portal does not have all the services or all the service application running on its own local servers. Not necessarily. The portal can be in a Yahoo portal, but all these services might be developed in different diverse platforms in using diverse programming languages, but they are accumulated at one portal application layer, and users can access horoscope and all this. So middle layer and application layer. But when we talk about the 7-layer model, it talks about people and processes and application. Now here, edge nodes are important, and then connectivity. After connectivity, edge computing, data accumulation, and data abstraction. Now this 7-layer this model, which is formally launched earlier by Cisco and then been adopted as a specification. This is the central theme for our discussion. So 7 layers of Internet of Things, it makes the IoT solutions comprehensive. So with this, let me start this 7 layers model. Now I told you we are aware with one another 7 layer model which we call OSI reference model, which has made this computer network a very successful technology paradigm. Now we are discussing this 7 layer model of IoT. If we carefully observe this slide, you can see the bottommost layer is all about physical devices and controllers. The things in IoT is, and we will discuss each of the layer and their functionality in coming slides, in the following slides. So physical devices and controllers are there, and these physical devices and controllers are the things in IoT. Then the second layer actually talks about connectivity. And when I say connectivity, it has got two major points: communication part and processing units. And then I talk about edge computing, data element analysis and transformation. I may have 10 sensors in one room, but I may just aggregate the data and may send it to the upper layers. Transformation, it is also been taken care by this edge computing. Then data accumulation, layer number 4. It's all about storage. So lower 3 layers is data in motion. As you move upward in layers, it is data at rest. It's been almost 20 minutes. Am I audible, sir? Hello? Okay, sir. Thank you. Thank you. So data accumulation is layer number 4, and then comes data abstraction, that is aggregation and access. It has got its own process, inferences and business meanings, and then comes applications. Applications are majorly like reporting. There are 3 major categories, or there are 3 major sections or sectors of developing applications. One is for reporting purpose, analytics part, and the control part. And then there are collaboration and processes involving people and business processes. So as I move downward, it is more of data in motion. I'm capturing data, I'm sensing data, I'm periodically fetching data, uploading them. So it's data in motion. As you move upward, it is data at rest. So with this brief, let us now, what does this reference model gives us? It gives us simplicity, clarity, and identity. It standardizes. So this reference model breaks down complex systems so that each part is more understandable. Second, these reference models helps us to provide additional information so that we can precisely identify levels of the IoT, and we can establish common terminology for professional developers or application developers. Then these reference models identifies specific types of processing is optimized across different parts of the system. Then this reference model also helps us to standardize, because I told you that we need to standardize the protocols, the rules, and then I can develop products accordingly. And that we have already done successfully with our TCP/IP, with our HTTP, with our OSI reference model. Now we are going to replicate the same stuff with IoT reference model. And that's why IoT architecture has a very prominent role of this IoT reference model, which we are right now discussing. So it provides first step in enabling vendors to create IoT products that work with each other. There are no vendor. See, it has to be standardized. Second, there should not be no vendor lock-in, because vendor lock-in is one major stuff. If I have 7 sensors in a room measuring 7 same or different parameters, and if these sensors are not getting integrated, or if they are not at the same level or layer, development wise it is not needed. But yes, passing on the information, yes, they need to be connected, they need to be collaborated. If they are not, if they do not have collaborative capability, then it is going to give a lot of issues in developing the IoT solution for that room temperature or for that room related stuff. So standardization is very much important. Then the another advantage of this reference model is it organizes, it makes the IoT real and approachable, simply instead of simply conceptual, because we are going to create products. We are going to create protocols which will help us to create products and give us results, give us benefits, advantages. So IoT reference model does not restrict the scope of or locality of its components, because lot many people have a lot of confusion at this protocol works at this layer, or no, it should not restrict the scope. Like physical perspective, every element could reside in a single rack of equipment, or it could be distributed. I can have a lot many elements in part of the single rack or single rack of equipment, or they can be distributed also. But in either of the case, their functionality and their efficacy should not get affected. This model describes how tasks at each level should be handled to maintain simplicity. We know this because we are quite aware with OSI reference model. It allows high scalability. Now this is something which is very important. High scalability and ensure supportability. In IoT, data flows in both directions. In control pattern, control information flow from the top of the model. Data actually flows in both the direction. So this is, the model is based on information flow, and you can see security is at the all layers and all levels. Control flows from top to bottom. Data flows in both the directions. Policy management and policy decisions are again from top to bottom layer. If we again analyze this, lower layers are more event based, upper layer are most query based, business intelligence, accumulations, aggregation, inferences, that's why query based. At upper layer, data is at rest, and at the lower layer, data is in the motion. Lower layers, sensors, actuators, connectivity, it's more of real time, and upper layers it's more of non-real time. So let us try to understand the first layer or the first level, that is physical devices and controllers. So physical devices and controllers, they control multiple devices. Now these devices are actually the things. In IoT, the things are nothing but these physical devices. They include wide range of endpoint devices, and these endpoint devices, these are the leaf nodes, the leaf devices. They are responsible for sending information and receiving information. This list of devices is already extensive, or they will keep on increasing. They will keep on getting added. These devices are diverse in nature, and there are no rules about the size or location or form factor or origin. Form factor is very important, keeping the development in mind. There are certain devices which will be size of the silicon chip, and there will be certain devices which will be as large as vehicles. So when I say things, it's, yes, majorly we think about sensors and all this, but not necessarily they are always tiny in size. There are certain devices which would be very large, and there are certain devices which would not be so large. They can be medium size, or they can be very small size devices. The IoT must support the entire range. Hundreds and dozens of even these device manufacturers are there. There are many device manufacturers for these temperature sensors. There are many manufacturers for these boards which supports multiple devices. So this is all about physical devices and controllers. You can see here the camera, the sensors, the smart meters, the industry environment. Now, there is a very peculiar understanding of these devices. These devices are capable of analog to digital conversion as required. Second, they should be capable of generating data. If they are only sensing the stuff, but if they are not capable of generating data, I don't think it is going to serve the purpose. And they need to be being queried or controlled over the internet. They need to get connected. Now, when I say network, it's not always internet, because I told you that there are non-IP things, but through ZigBee, through RFID, through LoRa. So there are so many protocols, there are so many standards through which I should be able to query them. I need to be able to fetch the data, and I need to be able to control them. So if these capabilities are not there, those devices are not going to serve the purpose. So there are sensors, devices, machines, intelligent edge nodes. There are certain machines which has got certain edge nodes, and these edge nodes actually takes care of this giant equipment, like the car manufacturing line. Level 2 in this model, IoT architectural reference model, is about connectivity. Communications and connectivity are concentrated in one level, that is level number 2. Now this is important. When we discuss OSI reference model, we discuss data link layer, we talk about LLC and MAC, logical link control and media access control, and there are and this data link layer in OSI reference model, that is the network model, has its own flow control, error control kind of stuff. Here you can see communications and connectivity. So the most important function of layer 2 is reliability, timely information transmission, like between devices and the network, across network, eastbound or westbound, and between the network, that is northbound or southbound. Now this eastbound and westbound at the same layer, northbound and southbound, it's all about this, which will come in the next level or layer. So between devices, machine to machine, because when we talk about IoT, when you refer IoT material, reference material, you will read these lines: device to device communication, device to cloud communication, cloud to cloud communication, and cloud to device communication. So device to device communication and device to network communication is taken care by this connectivity layer. That's why it is responsible for communications and connectivity. Across network, so timely information transmission is there, but this transmission should be between devices, across networks, and between the networks, that is level 2, and low level information processing occurring at level 3. So between network level 2 and level 3 also. So this is an important point to remember when we talk about level 2 of IoT architectural model. One objective of the IoT reference model is communications and processing to be executed by existing networks. IoT reference model does not require or indicate creation of a different network. It relies on existing network. Now this is I highlighted when I started my session. I told you that we are in the era of evolutionary technology. Backward integration, backward support need to be there. Forward-looking technology is always welcome, but it needs to support the existing standards, existing protocols, existing network types also. That is evolutionary technology. Revolution is all about remove the older one, replace it with the newer one. No, this is evolutionary technology. Local area networks still can be there along with in a very coexistence with IoT network. Personal area network can integrate with IoT. So that is evolutionary technology. We do not say that create a different network. It relies on existing network. And this is a very important point to remember when we talk about communication and connectivity at level 2. So here in this slide, you can see the level 2 functionality focuses on east-west communication, communication at the same layer or the same level. So this connectivity includes switching and routing, translation between protocols, security at the network level, and reliable delivery across networks. So a lot of things, lot of parameters, lot of objects which I am fetching, which I am sensing, which I am inferencing need to be communicated using various implementation protocols in a reliable manner across the network. So it has to take care about the switching part and the routing part also. This layer or the devices, the major devices or the boards which are work at this level need to have the networking analytical capability also. If they do not have this networking analytical capability, there are issues. Think about a farm where I have a lot of sensors and I'm measuring the humidity, I am measuring the soil moisture. And if these sensors are there in a farm and there is a server or there is a laptop which is sensing this humidity and soil moisture and soil type, and if they do not have the networking analytical capability, then my project is not going to succeed. Think about a car manufacturing where security at the network level is not supported by the devices which are there in the car assembly line. It is not going to succeed. So I need, and if I have 5 farm clusters being connected by these sensors and all this, and if the central switching and routing capability is not there, I cannot infer meaningful data because of the failure of switching and routing. So if the switching capability is not supported at the central location, because I might be thinking about the European farms or the American farms where there are 1000 acres of land and they are using IoT solutions for that. So when I deploy the devices, the soil moisture sensors and all this, I need to erect the switching capability part in this 1000-acre farm also. So that is important. Layer number 3 is about edge computing. Conventionally, we used to call it fog computing also. Now, this layer is driven by the need to convert network data flows into information. Now, what is the meaning? Information means something which has higher level of meaning, which is more suitable for storage and higher level processing at level 4. So this level 3, this local processing or local pre-processing will help me to convert this collected data or the collected data flow into information. That means I might have 50 sensors sensing various 4 categories of parameters. But if I'm not converting this network data which is coming every 5 seconds through these sensors, 50 sensors, if I'm not converting into information, then it's not suitable for me to for storage and higher level processing at data accumulation purpose. So layer 3 is all about converting network data into information, and this data is suitable for storage and higher level processing. So layer 3 focuses on high volume data analysis part and transformation part. So transformation is there and data analysis is there. Now the basic tenet of this reference model is intelligent systems initiates information processing as early and as close to the edge of the network as possible. Because there are IoT solutions, there are companies which provide like Cisco and all this, which provides IoT solutions for very giant business conglomerate. Now in those IoT solutions, there are millions of sensors. And I cannot fetch or whatever I sense, whatever data I sense, if I try to put all those data in cloud without pre-processing or without some kind of transformation, my network is going to fail. My IoT network is completely going to get failed. It's not visible. So I need to have this fog computing, pre-processing computing as early as possible and as close as possible to the edge of the network. I try to, so I can have millions of devices or things in my industry environment, and I'm fetching a lot of billions of data every few hours, and I do fog processing first, and then I proceed with data accumulation and data aggregation then after. So information processing should be as early as possible and as close to the edge of the network as possible. That is very important point for this layer 3 or level 3. This is sometimes referred to as fog computing also, and level 3 is the place where fog computing actually takes place. There are many examples of fog computing or level 3 processing or edge computing. What are the activities being taken care at this level 3? Number 1, evaluation, evaluating data for criteria, whether it should be processed at higher level. Formatting, so reformatting data for a consistent higher level processing. With temperatures you can understand, with pressure gauge parameters you can understand this reformatting of data. Expanding and decoding, so handling cryptic data with additional context. Reduction or distillation, reducing or summarizing data to minimize the impact of data and traffic on the network. Because I need to summarize, I need to reduce. I cannot, as I said, if I have 10,000 sensors and if I'm fetching data every 5 seconds, I cannot completely deploy this data on the network. My network is going to get failed. So I have to think about the impact of data and the impact of data on the traffic of the network before proceeding with the higher level processing systems. And the last important activity which is taken care at level 3 is assessment, determining whether the data represents a threshold or alert. If it is not approaching the threshold or if it is not approaching the alert, not necessarily that I pass on the data all the time to the upper layers. I need to redirect it to the additional destinations. So this is all about fog computing. Data filtering, cleanup, aggregation is there. So please remember, filtering is important, cleanup at level 3 is important. So if I'm devising a product for level 3 for fog computing, I have to take care about cleanup, I have to take care about aggregation, I have to take care about thresholding, because there may be multiple thresholds with those 50 sensors which are actually measuring 5 parameters. So I can have 5 parameters and 50 sensors, which is a very trivial example, but still threshold is something which is very important. Event generation, what kind of event is getting triggered, because it's not always that all sensors are periodically sensing only. There are some event based sensors, or there are certain event based actuators which are actually doing the task. So level 3 functionality focuses on north-south communication between upper layers and lower layers. So once we understand this second and third, now this figure actually talks about Internet of Things reference model. It is all about connectivity and data element analysis example. So here you can see that there are devices, there are boards, there are sensors, and which are various protocol based. And then there is a connectivity stuff, which is a protocol plugins. Then you can have device APIs. So there are protocol plugins and device APIs, which the professional developers or the software developers have created. They're fetching the stuff. And then there is an edge computing. And this edge computing actually have its own API also. There is a data interpreter reference. And this IoT service, what are the IoT services at the edge level? Registration, transformation, monitoring, semantic, and this edge router or gateway actually helps us to provide this data to the higher level, that is intermediate nodes, and then after it goes to data centers or IoT data consumer part or at the cloud through LAN or WAN. Level 4 is about data accumulation. So the data is in motion prior to level 4. Now data is moving through this network rate, and organization determined by the devices generating the data. Data in motion, at which level, at which speed it is coming, how periodically it is coming. Is it coming every 10 seconds or is it coming once in 1 hour? And it is an event driven level. This level device do not include computing capabilities themselves. Some computational activities occur at layer 2, like protocol translation or security policy and all this. Additional compute tasks can be performed at level 3, that is packet inspection and all this. We have already discussed this. So data accumulation is, networking systems are built to reliably move data. And when I'm moving it, the most important stuff is at which speed, at which motional speed the data is coming, and what is the periodicity or frequency of that data. And when I'm bothered about this, at data accumulation part, this data in motion is converted to data at rest. This is the main task, level 4. So to do so, level 4 processing is first level, jahan pe what we try to, data must be persistent. Should data be kept on disk in a non-volatile state or accumulated in a memory for a short-term use? Whether I'm putting it for a large storage purpose or for a long storage purpose, or it is for a short-term use. What will be the persistency level of that data? The type of storage needed, what kind of persistency, depending upon the persistency requirement of the file or a relational database, what kind of storage I need at this level. How am I going to organize the data? Because at data accumulation part, how am I going to, because the data, majorly 90% of the industry generated data is non-structured data now. So structured data, semi-structured data, and non-structured data. Structured data, we know database, rows and columns, and it has got its own form of metadata also. Semi-structured data, XML, JSON files, these are semi-structured data. And unstructured data, 80 to 90% of the data which now being generated, they are unstructured data, the data. So how am I going to organize this data? The data must be recombined and recomputed. So there is combination, recomputation, aggregation involved at layer 4. And you can see here, event filtering, event comparison, event joining for CEP. These are all very much part of event aggregation is there. So there is a event generated data, and we are transforming into query based data consumption. So we are preparing the data for query based processing, and that's why it's called data accumulation. That's why the word storage is being given. So this level, data accumulation level, actually converts data in motion to data at rest. It converts format from network packets to database relational tables. If it is a structured data, if it is a semi-structured or unstructured data, we need a different mechanism. It achieves transition from event-based to query-based computing. That's what we already discussed. Data abstraction. Abstracting the data. Abstracting means at looking at the data at one higher level and working accordingly. So information integration is very much part here. It creates schemas and views of the data in manner that application want. Now we are preparing the data for application processing. We are creating schemas, we are creating different views. People who have gone through the subject called database management system, they can understand these various views of data. It combines data from multiple sources, simplify them for the applications, and to simplify them, I need filtering, projecting, reformatting data. That's where I can take the business intelligence decisions in higher levels, because I'm preparing data and I'm projecting them. So if I'm gathering data for business analytics purpose, right data in right format to right person at right time needs a lot of filtering, selecting, projecting, and reformatting of data, which actually occurs at data abstraction phase. That's the central theme of this data level. It reconciles different data shape, format, semantics, access control, and security related stuff. I'm going little bit fast because we already, sir, still I have 3 to 5 minutes. Okay, sir. Because I'm little bit going quite fast, so I thought, yes, because we are approaching 1 o'clock and then there is a break, and then after the subsequent sessions are there. So data abstraction is all about ERP, HRMS, CRM. So what we try to do is we just try to, data abstraction is all about putting value to the data, putting meaning to the data, putting contextual benefit to the data. If I'm not deriving any contextual or event-based meaning to the data, it is difficult for me to understand the data. And the sixth layer, that is the application Now here actually comes, we are preparing data here in the previous slide, though here we protect data with appropriate authentication and authorization. We go with normalizing data, denormalizing data. We try to index data. Indexing is one very important stuff with social media text, with social media data. There are many algorithms, there are many methodologies which are being employed to indexing the data. So Internet of Things has a lot of stuff to indexing. Data which is very structured. There's an RDBMS system where queries can be fired. We can derive a lot of business meaning out of it. So it is always been there at level 5. Now once we have derived these benefits, now we are approaching application part. Now applications are basically three kinds of categories. One is control applications. The applications which will give the commands, or the applications which will send appropriate commands to the actuators to take certain corrective or control measures. The second level of applications for this IoT architectural reference model level number 6 is vertical and mobile applications. There is a whole set of industry verticals I can create. Now, why am I creating these industry verticals? These industry verticals is actually taking benefit. See, I can have 500 salesmen taking care of 700 locations, and these 700 locations can have more than 1.5 lakh objects or things connected. And I can create one industry verticals. And I no longer need 500 salesmen or business people visiting these 700 facilities or locations every weekend or once in every week. I can create a complete industry vertical application, and this industry vertical can empower me to take business decisions sitting at one location. I can create mobile applications. These mobile applications can get integrated with my existing locations. And the third category of application which I can create, and this is a very big major market where machine learning and big data analytics and Hadoop and all this is involved, is called business intelligence and data analytics. So what is a business intelligence? One line which I am telling you since I have told you a couple of times, right decision to the right person at the right time in the right context is business intelligence. A lot many consumer goods company is actually developing a lot of or pumping a lot of money to create this business intelligence decisions softwares. There are analytics software which are a major part. So level 6 is an application layer where information is interpreted. Information interpretation actually takes place. An IoT reference model does not strictly define an application. Application can vary based on vertical markets, the nature of device data, the business need. For a consumer goods company, the business need would be different. For a chemical factory where security or the hazardous chemicals are taken care, the business need or the criticality of the sensor data or the things data is different. Some applications, as I told you, would be on controlling devices. There are certain applications which are for some kind of pattern recognition, some kind of business pattern recognition. There are certain mission critical business applications for which if I'm developing, the analytics have different levels of criticality. So based on these levels, actually I create this. And the 7 level or layer of IoT reference model is collaboration and processes. So this collaboration and processes actually involves people and business processes. So the difference becomes particularly clear at level 7, collaboration and processes. Because the IoT system and the information it creates is the little value unless it yields action. If it is not giving me any kind of action, if it is not giving me any kind of inferences, I don't think it is serving the purpose. So this action requires people or processes. When it is processes, it is more of machine to machine interactions. Multiple people use the same application for a range of different purposes. You, through your mobile devices, you are actually coming across a lot many applications where uh, the purpose is different. It varies from person to person, but still the application is actually serving the purpose. So creating such kind of application based on IoT reference is really a very challenging task. So objective is not the application, it is to empower people to do their work better. That's where I told about QoE, quality of experience, because we are empowering people. We are not only streamlining the applications or application development part, we are trying to empower people to do better work, to take better decisions, to take better business intelligence decisions. So application level 6 gives business people to write data, the same stuff which I'm telling you. So I can take better decisions when it is collaborative part. So I can create applications and analytic part at level 6 which can empower people. So these are all about these 7 layers. Security in IoT is a separate area, but I have included because security at every layer is involved with IoT. So I have to secure each device, I have to provide security for all processes, I have to secure movement and communication of the data at each level, whether it is north southbound or whether it is at the same level. So this is all about the security aspects. At lowest level, I have to secure the content. At level number 4, I have to make the data tamper resistant. At level 5, I have to make secure storage. At level 6, if I'm addressing the security issue in IoT, it's more towards authentication and authorization. If level 6, I'm addressing the security aspects, it is more towards identity management through softwares. If I'm addressing security at connectivity level, it is secure network access, let it through hardwares and protocols. And at level 3, that is for computing, it is secure communication. So security has different meanings, but yes, security has at all levels or IoT exists, and these are the various points to remember. And this is the slide, this is the last slide of my presentation. It talks about IoE, Internet of Everything. That's the next step after IoT, where things are there. Along with things, there is data, there is people, and there are processes. I had a certain case studies also, but because of this is the connected bus, and you can see the number of connectors, sensors, digital screens, digital cameras, and all this. This is a oil and gas case study where modular solutions exist for IoT solutions. And I end my session with this quote, a bit funny one. I will not be impressed with technology unless and until I can download food from the internet. And this is one of my favorite. He who opens a school door closes a prison. It's a very well thought out quote from Victor Hugo. He who opens a school door closes a prison. So with this, I conclude my session. Thank you very much. Thanks for being part. As sir said, I welcome queries and questions or suggestions from participants across the nation.
Yes, sir. Yes, sir.
Sir, it is sir, IoT for GEC are revised. Yes, it is already been uploaded.
Good afternoon, everyone. I would just like to say a few instructions which are mandatory for this FDP. First of all, e-certificates will be provided to the participants who are having 80% of participation and who are scoring above 60% of marks in the quiz. So that is the first thing every participant should take care of. The second important thing is everyone is requested to keep your microphone muted during the sessions so that our experts can deliver the lectures at the best and you can get the best from this FTP. And during the question answer session, which is organized after the sessions, when the session gets over, there will be question answer session. At that time, you can just unmute your mic and you can ask the question. So that is the second thing you need to take care of. And the third thing is the attendance records will be automatically fetched from the Microsoft Teams. So the Teams itself is having that facility that whenever a participant is getting logged in, logged out, everything is getting recorded in the Teams. So just make sure that you attend all the sessions and your participation is 80%. Okay, that's all. And I think, sir, we should end this session now.
Yes, yes, sir. Yes. I'll read the question first for Madam Anupama, and then I'll try to reply the. As a beginner, how to get started? As I am from EHTC background, that is EC background perhaps. So I have some knowledge of sensor, but how to get into the networking part? Okay, Madam, thanks for raising this question. Pedagogically, the books are available for IoT, but practically speaking, if you just want to get connected, if you are little bit aware about the sensor part, what you can try to do is you can just try to connect the sensors with this Raspberry Pi or the tools or the boards available. And networking, see, networking actually comes into picture when you are going one level upward. That means when uh, multiple devices are there and you are trying to capture variety of parameters from these multiple devices. And I am pretty sure that the sessions which are going to be there this afternoon and tomorrow, you will get practical exposure of how to sense these parameters and how to store them or how to network them. Now there are two ways of networking. If I look at your networking part, there are two ways. One is networking of the sensors, which these sessions will take care. The second one is networking of the data which you are fetching. Now the data which you are fetching through this, there are protocols. So if your devices are taking care of that COAP protocol or MQTT, then obviously your Raspberry Pi board will uh, you can connect this with your laptop or with your system, and it will take care of this connection. Because nowadays a lot many boards or lot many circuit boards or lot many IoT boards are there which are on the appliance level. Now when I say appliance level, it is actually taking care of the local storage, or it is taking care of the plug and play kind of feature. So when you are having this plug and play kind of feature, yes, it is very clear. If you want to start from raw, that is like if you just want to deploy the sensor itself and then try to sense and then try to create the networking environment for your any kind of research purpose. For that, you need to get it connected to this system, and you need to initiate very basic data transmission protocol to store this fetch data into the local system, that is the local computer or the local node which is connected to the row sensors or a couple of sensors or a group of sensors. So I hope I have addressed the question, and sir can throw more light onto it perhaps. हाँ सैयद साहब बोलिए जी. Thank you, sir. Thanks for the opportunity. Thank you all.
Hello.
Yes, Mr. Vinay Prasad. Mr.
Yes,
Vinay
sir.
Prasad. Yes,
Yeah,
yes, sir.
Am I audible, sir?
Yes, sir. You are audible, sir.
Okay. I have a slight question on this, what you just said about that IoT architecture.
Ji, sir.
Yeah, can you explain about the edge computing, that how you could implement that over an IoT platform?
Yes, sir. Sir, edge computing is all about, I already practically, theoretically explained that we are having devices, and these devices are actually fetching the data, and they are fetching the data either event driven data or the periodic data. So if I already given you the example, suppose I have one industry setup which has 50 sensors, and these 50 sensors are actually trying to these 50 sensors are actually trying to gather 5 types of parameter, because some of them are temperature sensors, some of them are pressure gauge sensors. So there are 50 sensors, so 50 data. Let us take the example, every 5 seconds they are fetching the data. Now when they are actually fetching the data every 5 seconds, and there are 5 parameter types, there are 5 types of parameters. Out of these 5, let us take the example that there are 3 temperature type parameter and there are 2 pressure type parameters. So edge computing actually, what does it do? If that data which you are fetching every 5 seconds is not that much critical, so for 1 minute you are actually fetching 12 inputs, temperature inputs. So 1 minute 12. So 12 into 60 is 720. So 720 into 50, that comes out to be somewhere around 10,000 stuff data. Now you are not going to directly upload it. So what we try to do is we just try to aggregate the sensors, sensor data. So if there are temperature data, there are 3 types of temperature. So all these 3 types of one type of temperature, we just try to take the temperature values. We just try to sum it up for every 4 minutes. So that comes out to be 5 seconds or 4 minutes. That comes out to be 40 values. So there are 40 temperature values, and these 40 temperature values are aggregated. You can take the mean or you can take the average, and this average value will be uploaded to the higher level. So instead of fetching data, instead of passing on data every 5 seconds to the upper layer, what you are doing is every 4 minute data is actually uploaded to the higher level. So from 5 seconds, what we are going to 4 minutes. So 5 seconds, every minute there are 12. 4 minutes, 12 into 4, 48. So instead of passing 48 values, I am just passing one value. So that is called edge computing. So I am trying to process data as close as the data accumulation device. जहाँ पे मैं data fetch कर रहा हूँ, जहाँ से मैं data read कर रहा हूँ, जहां से मैं टेम्परेचर या प्रेशर रीड कर रहा हूँ वहीं मैं उसका एग्रीगेशन कर रहा हूँ फोर्थ एट द लेवल ऑफ कनेक्टिविटी लेवल 2 और लेवल 3 में, तो उसको कहते हैं फोर्थ कंप्यूटिंग या एज कंप्यूटिंग. Am I
Okay.
clear, sir?
Yes, sir. Sir, edge computing is something an infrastructure which would be lies between your cloud and the node, the physical node, right?
Yes.
Where we would be planning to mitigate the delay between them. So the time at which that node it takes time to upload the data to
Sir,
cloud.
you try to mitigate the delay depending, say you take the mitigation of delay decision not based on the location, because edge computing is it's an intermediate processing.
Yes, yes,
I
yes.
should not say it's
I
pre-processing. It's an
yeah,
intermediate processing.
I agree,
Am
sir.
I
I
right?
agree.
So when you are trying to intermediate processing, your mitigation decision is based on the criticality of the data you are sensing. If
Correct.
that temperature which you are sensing is very critical,
Okay.
you have to pass on the data every 5 seconds. But if it is not critical, then you can go with averaging or the mean value, which I give the example like every 5 seconds I am sensing the data, but मैं जो pass कर रहा हूँ that is every 4th minute. So I need to develop an Android, I need to develop a program which will do this kind of stuff, and I have to deploy that program at the intermediate level for intermediate processing.
So what will be the current open issues in an IoT field, sir?
Sir, the major issue in IoT right now is the vendor locking. So
Okay.
it's a general. I'm not giving specifically. So it depends upon the case study. It varies from case to case. But the issue which right now we are having is like vendor locking or compatibility issue, because sir, there are though the Raspberry
Interoperability.
Pi and these people have tried to create the open or universally accepted parameters and stuff, but still there are issues like vendor lock-in or compatibility or the parameter transformation. So when you take care about parameter transformation, I hope if vendor locking is not affecting or adversely affecting the parametric transformation, then the mitigation part is taken care of.
Okay. Sir, how the scalability issues would be addressed by what the present IoT architecture would be?
Sir, scalability, to address scalability issue, this edge computing is required. That is the very intermediate. That is the very uh, I should say very practical solution, because scalability is obviously a very big issue. That's why I give the example. Every 5 seconds, 50 sensors. Every 5 seconds you are fetching the data, and that data comes out to be 10,000 every minute or this. So scalability address करने के लिए हम edge computing कर रहे हैं, and it does not address only scalability part. It also addresses other part like formatting, uh, mitigation, and network traffic, because network traffic is also, because scalability, if my network traffic does not get handled well, I cannot provide a scalability solution. So that's why for computing is there.
Thank you, sir. Thank you.
I hope I address.
Yes, 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 sir. Thank you.
Sure, sir. Yes, definitely, sir. GG, sir. G, sir.
Thank you, sir.
Thank you. Thank you, sir. Thank you, and happy learning to all. Thank you.